let's go over this question. We have a curve defined like this. This is the same parametric format that I described in the previous video. And the part A of this question is to show that this curve has two tangents at 30 point. So 30 is on the x-axis, and I will mark it with this color in here, right? So now in this graph we have the 30 point in here within the x-axis, and this is the x-axis and the vertical axis is the y. Now we are supposed to show that this curve represented by the given formula. Now still we don't know its exact shape, okay? But we have to show that it has two tangents at the given point. Now can a function, or I mean a curve, has two tangents at a given point? Say now the thing is, now most of the times the curves that we described in calculus 1 are actually functions, right? So if it is a function like this, at a certain point it will only have a single tangent, right? But suppose we have a curve, right? If we have a curve like this, right? Now clearly this is not a function, right? Because now for this x-axis, x coordinate, you have two y coordinates corresponding y coordinates, right? So that violates a property of a function. But anyway, for this curve, right, now in this intersecting point you can see that there are two tangents like this, because basically you have two curves crossing each other. One curve is this one and the other curve is this one, right? So at that intersecting point you will get two tangents. And also now say if we choose a point like this, right, for this particular, this corresponding x value, since you have two y values, you will get two tangents. So existence of two tangents is possible when you have some weird shapes like this, right? So you have to clear that up in the beginning, okay? Right, so now we have to show that it has two tangents, and also we have to find the equation. Now in order to compute tangents, first of all we need to compute the derivative, and we did that in the previous video, right? And about this 30 point, now the y coordinate of our given curve is expressed like this, right? So we can factor out a t and rewrite it like this, right? So by looking at this equation, you can say that at t equals 0 as well as t equals positive root 3 and at t equals negative root 3, for all these three values, the y coordinate will be equal to 0. For all these three values, the y coordinate will be equal to 0, right? And how about the x coordinate? Now when t is equal to 0, x coordinate will be equal to 0, because x is given as t squared, right? So according to this formula, when t is equal to 0, x will be equal to 0, right? And when t is equal to positive root 3 as well as for negative root 3, the x value will be equal to 3, right? Now, so at this particular t value, the parametric value, that is root 3 and negative root 3, you can see that x is equal to 3, positive 3, and y is equal to 0, right? That means this 3, 0 point is obtained from t equals root 3 as well as when t is equal to negative root 3. Now remember, they have not mentioned any restrictions for this parameter, for this t variable. The parametric variable is not restricted within this problem. So this t variable can of course take negative values, right? But if it was some sort of a physical example where t represents the time, if t is time, then there is no point of talking about these negative values. But within this problem, they have not made any restrictions, so we can of course consider the negative values also for the for this third variable t, right? Okay, and that's something you should notice first, right? For this 0.30, we have two t values, if you substitute both these t values, you will get this coordinate 30, right? Okay, and to compute the slope, right? To compute the slope, now there's another thing you should notice. Slope means that is given by the formula of dy by dx. Now with this equation that we derived with the help of chain rule, and I did this in the previous video, you can see that the slope of dy by dx, that means the slope of this xy relationship, is expressed with the help of t. That is, in other words, at a certain point, if we know the corresponding t values, we can compute the slope at that particular point. Now you should kind of understand this one, because now this is the gradient or the slope of y with respect to x. That means we are plotting it in the x coordinate plane of x and y, right? Now within this coordinate system, we don't mention anything that relates, we don't have any axis that represents the t, right? But still, due to these parametric conditions, we were able to write down a relationship for dy by dx with the help of t, right? So now, and also now, as we are supposed to compute the tangents at this point, we saw that there are two t values, namely square root of 3 and negative square root of 3, right? For both these t values, you will obtain the given 0.30. In other words, now this itself says that you will have two tangents, because you have two t values that corresponds to this point. That means you can compute two derivatives corresponding to each of these 2 points. So basically what we have is, and when you compute the derivatives, it will you can see that the derivative of y with respect to x at t equals root 3 will be equal to root 3, and by doing a similar calculation at negative root 3, you will get the derivative also to be equal to negative root 3. Now these values becoming equal is totally a coincidence. Okay, it is not at all required for these two values to be equal. Okay, this is just a coincidence, right? Okay, so now we have computed the derivatives at each of these 2 points, where both these points corresponds to our curve at 0 point in the xy plane, right? And now we have to find the equations of the tangents as well. Now if we know the slope, how are we going to find the equation? We can use this relationship, right? Y minus y naught equals x minus x naught. Now m represents the slope. So when the slope is equal to root 3, the equation, and now remember our x naught y naught point is the 0 point that they have given, right? And if the point and a slope is given, this is the way that we find the equation of a straight line, right? And remember, the tangent means it's just a straight line with a slope, with a certain slope that we find through dy by dx, right? And since the point is given, this is, now we are left with finding the equation of a straight line when a point and a slope is given, right? So this is the required equation, and you can see y naught is equal to 0 and m is equal to root 3 because we are in this case, and this is equal to this one, x minus 3. And when the slope is equal to negative root 3, then the equation will be like this, right? Now see, all the other terms are very much equal, but not the slope of the tangent. So this has a positive slope, this has a negative slope. When a certain straight line has a positive slope, it takes this shape, and when it has a negative slope, it takes this shape. So that means at this particular point, you will have two straight lines that goes like this, right? One is like this. I will change the color to blue, and the other one will be like this, right? Yeah, so that means we will have now, for this we need some more data, but we can make some sort of a educated guess that the curve we consider will take a shape of this nature. Like here you will get some sort of a weird shape we still don't know, and then it will again go like this, because remember, this is the negative slope, right? So it corresponds to the negative value t equals negative root 3. That means at t equals negative root 3 at t equals negative root 3, the curve must go through 0 point, right? And when the value of t increases, the curve will take a certain shape, right? Sometimes curve might change its direction as well, right? We don't know that. And then now the curve can even go like this, okay? But if we compute this graph specifically, you can see that the curve takes a nice shape like this, right? So what I want to highlight here is, now these two are the tangents representing the derivative at 30 points. So now with these data only we cannot figure out the exact shape. Okay, so but at least for the time being, what you should mainly focus is about the, not about the shape of the curve, but about these tangents, about these two tangents that that are there at this single point, which is a very special case. I mean, when it comes to parametric equations, it's it's a just a usual thing, but for the graphs that we have dealt before in calculus 1, we did not have this sort of a thing, right? So the answer for this part of the question will be show that E has two tangents. Now we already proved, or we already calculated both equations. So basically we have shown that it has two tangents which can be expressed in this equation. And so that means this represents this tangent and the other equation represents this tangent. And in the next video we will focus on some more theory regarding this question.